Hello, everyone. Thank you so much for joining our today's celebration of the International Day of Light. And I'm Dr. Sajid Muhaimin Chaudhry. I'm the chair of the IEEE Photonic Society Bangladesh chapter and the president of IEEE OSA Bangladesh section. So today is the first webinar that two of the organizations have, which is firstly the Optical Society Bangladesh section. This was established in 1st of May this year. We have successfully petitioned it and we have a virtual presence. Please stay connected with us. Another organization we are inaugurating today is the IEEE Photonic Society Bangladesh chapter, which is under the IEEE Bangladesh section, and this is our web presence. Just to give you a brief idea about the International Day of Light, which is the Light Day 2021. It is celebrated every year on May 16th. And this is a successor of the event of International Year of Light, which was announced in 2015. And 2015 marked the 1000th anniversary of the birth of optics. And 1000 years ago, Hassan ibn Hasim, he wrote a book called Kitab-i-Manazir, or Book of Optics, that treated various optical phenomena with the accuracy of scientific method. And he successfully showed how the human eye works by receiving optical signal or light from outside objects. And this book was written in 1015, and 2015 was the 1000-year anniversary of it. And UNESCO recognizes a lot of anniversaries of this, like the wave nature of light discovered 200 years ago, Maxwell's electromagnetism, or unifying the Einstein's general theory of relativity with light, and the first successful launch of light through an optical fiber. Since 2015, it is celebrated yearly 16th May, and 16th May 1960 was the first time when Theodore Meinman tested his laser. So we also want to celebrate this day in Bangladesh, and on behalf of Optical Society Bangladesh section and IEEE Photonic Society Bangladesh chapter, I would like to welcome you all to our inaugural webinar. I'm extremely glad that we have Dr. Gururaj Naik among us. He's going to be talking about hot nanophotonics light with a phase transition. A little introduction about Dr. Naik. He's an assistant professor in Rice University, and he actually received his Master of Engineering from Indian Institute of Science, Bangalore, and he received his PhD from the Electrical and Computer Engineering Department at Purdue University. In a sense, in Bengali we call Boro Bhai, or he's my academic Boro Bhai, or senior, in a sense that he's the first PhD student of my PhD supervisor, Professor Alexandra Boltaseva. And after completing his PhD from Purdue, he joined the Rice University in 2016. Before that, he served briefly in Stanford University as a postdoc. And he received numerous awards from IEEE Photonic Society, or Outstanding Graduate Research Award, and a gold medal from Indian Institute of Science. And he has a stellar scholarly publication record, over 40 international publications, and over 8,500 citations. So without further ado, I would like to invite Dr. Naik to give his presentation today.
Thanks a lot, Sajid, for this initiative. I think I should congratulate you first for having this IEEE Photonic Society and OSA Photonic Societies established in Bangladesh and leading those efforts. And thank you all for joining this webinar session. I know I heard that, the country is under lockdown and the health situation is concerning, and I'm glad that you guys can still make it to this webinar at such a late time as well. So thank you. So today, let me share slides, what I'll be talking about. So Sajid just briefly mentioned, yes. be talking about hot nanophotonics, or light with a phase transition. So again, thank you for Sajid for the very kind introduction. So we did overlap at Purdue University, so where Sajid was, I should say, I probably overlapped maybe 1 year or maybe 1.5 years with Sajid when I was finishing my PhD while Sajid was beginning there. And the inspiration for optics, the beautiful introduction that he gave as a part of International Day of Light, I think that's exactly what inspired all of us to be scientists, learn and then contribute and then now lead research in this topic so that we can change the society for good. So that's what we all are inspired and aimed at doing. And here I present just one application of light where it can address a very important challenge that we currently face. So before I get into all the technical details, let's look at something more aesthetically pleasing. Okay, so this is just a picture, a scenery from a beach with sun setting. And of course, this is a very beautiful beach. I stayed in California for some time, again next to beach. Rice is in Houston, which is also next to a beach. And I'm sure, I think with in Bangladesh, you all have access to, at least maybe not too far, still nearby, you have access to beaches. So one thing that comes to my mind, of course, this is a nice picture, but as an engineer, as a scientist, what comes to my mind is if I look at this ocean, suddenly it appears that yes, the ocean levels are rising, right? So we have global warming, we have climate change. So that's a biggest problem, that one of the biggest problem that our society is currently facing. So how do we solve this? Can we have, as a scientist, contribute something that can make it better for future generations? And the solution also is in the same picture, right? So that's sun. So sun is just one form of energy which can solve this issue. So if you look at just many other renewable forms of energy, so clean energy is the future. And if you look at just in the case of US, renewable energy is really very fast progressing technology. So DOE, Department of Energy, here makes a handbook once in every 10 years. So this is 2014, still 7 years old. Yet it shows that renewable energy is very fast growing compared to many other energy industries. Okay, and then this is still old, where it was less than 10%, but now renewables is close to 15% of US total energy production. And out of them, we have two different forms that are very fast growing. So one is solar, the other is biomass. So geothermal, of course, and biomass. Wind has kind of saturated quite a bit, but solar is by most the fastest growing technology. And all of these, like solar, geothermal, or biomass, they all rely upon some form of heat or light. And if we know how to convert this heat and light to electricity, we just know how to work with renewables. So that's the problem that we have in front of us, and an opportunity as well. So what can we do? So if you look at just the current PV cell, like photovoltaics, silicon solar cells, so you see that the efficiencies are close to 22%, and you have a huge loss in efficiency. So the Corona efficiency, or the thermodynamic limit for efficiency with sun, is close to 95%. And we have far less than just 22% with silicon. So why is it? I'm sure, I think all of you have heard about Shockley-Queisser limit, but I think if you break the components of energy loss into something more substantially physical, we see that there are two phenomena which contribute for major loss in efficiency, nearly 40% loss in efficiency. And the first one of them is just with the energy of the photon. So sun is broadband radiation. So have infrared photons to all the way to UV photons, right? So infrared photons have much smaller energy, and UV photons have much larger energy than them. So when the energy is much smaller than the band gap of silicon, then that photon just remains unabsorbed. It just goes away. Nothing happens to it. So the energy it contains or it carries is just lost. So that's one component of energy loss or efficiency loss. The other component is when the energy is much higher than the energy than the band gap of silicon. Okay, if this is the band gap of silicon, then this excess energy that this photon carries, so this excess energy is dissipated as heat. Okay, so the electron that is excited deep in the conduction band will now just release or relax to the bottom of conduction band by just dissipating this excess energy as heat. So these two contribute to 40% loss in PV efficiency, right? So that's really huge. And if we want to overcome, push the efficiencies of solar cells higher, the only way for us to do is somehow deal with this multi energy photons in sunlight. So how do we do that? So this is in fact a very clean opportunity for nanophotonics because this is just spectral management. So when I say spectral management, um, it, it's about taking many different photons of many different energies, and then putting them together into some narrow band of photons so that we can handle, we can convert it to electricity efficiently. So how to do this? Okay, so one alternative we have is thermophotovoltaics. So here is the way thermophotovoltaics work. So think about, okay, you have this broad sunlight, a band of sunlight, and then now if you put a a PV cell, silicon or some other material in front of it, then the band gap is going to make it selective or efficient only for that particular wavelength. So what if you want it to be completely independent of wavelength? So just put a black body, okay? So something that is very, that doesn't distinguish the energy of photons and just absorbs. So black body does that. So by absorbing all the solar photons, this black body now converts light energy into heat. So black body becomes hot. So when it becomes hot, it emits again thermal radiation, just like sun does. Sun is just a black body sitting at 6,000 Kelvin. So any other black body would also do the same. So now this black body emission is going to be again broadband, mostly in infrared, okay, but still very broadband, meaning many different photon energies. So what's the point in going from one broadband source to another broadband source, right? So there is really nothing unless we do some trick. So this broadband thermal source or this black body emitter is actually in our control. So we can control what happens to it. Okay, so now just imagine that we put a filter that is ideal. So which has a small region in wavelengths where it allows photons to pass through. So that's its pass band. And if the photon has energy that is outside of this pass band, so either here or over here, the filter perfectly blocks it and then reflects and sends it back. And the black body will just absorb it. Okay. So what happens effectively is if the photon has energy that is in the small pass band of the filter, it would just come out. Otherwise, the energy of the photon is trapped in this black body just as heat. It doesn't get out. Okay, so what we did essentially with this technique is take broad wavelengths or broadband light from sun and then squeeze its wavelengths to very small band or narrow band here in the infrared that is given by the filter's functionality. Okay, so we effectively converted broadband to narrowband, which is extremely hard problem, but nanophotonics has us some solutions to do this, especially how to implement this filter and the black body as well. Okay, so now if you put a PV cell, then we don't have any problem converting narrowband photons into electricity. Why? So you know that if you take a photodetector, let's say you buy a LED, excuse me, a photodetector, and then you have a laser shining on your photodetector, then you know that it's very easy to convert this single or monochromatic beam, single wavelength beam from a laser into electricity very efficiently. Photodetectors, in fact, have quantum yields close to 100%, 99.5 or more. So it's we know the efficiency can be very high, and hence the overall this thermophotovoltaic TPV efficiency can be as high as 80%. Okay, so this is the really promise of thermophotovoltaics. So what has happened since then? Okay, so people just started out with thermophotovoltaics. This is not really something new. The scheme has been there for a long time, nearly 50 years now. Okay, so people have thought, okay, this is just some heat to electricity conversion technique. So why don't we use it on other things? Instead of just solar, if we, for example, use it say to extract heat from some radioactive sources like plutonium, we could power up Mars rover. Okay, so Mars rover previously used thermoelectric generators, which were just 2% efficient, very low efficiency. So if we have high efficiency TPV, then we could potentially revolutionize how we power up um, uh, this the spacecrafts, right? So this is going to be a game changer there. Many other applications, including even body heat power watches. Then more importantly, waste heat recovery is a big industry. Okay, so industrial plants, even jet exhaust for that matter, and industrial plants like fertilizer plants, they have so huge energy consumption, and nearly 20% of them is wasted. And this waste heat is usually a mid-grade waste heat. And if we can extract this, this would be worth 3 years of electricity just for Texas. And Texas is one of the largest states of United States of America. Okay, so this is a huge fraction of energy. So I just want to give you a perspective. It's true with many things, even all over the world, it's actually true, but more dramatic with countries like USA, where there are a lot of industrial production. Okay, so this is a huge opportunity. So where is thermophotovoltaics, and why haven't people used this? So what is happening with that? So here is what many demonstrations have done. So we need to build this ideal filter, right? So if you remember, we need this black body which perfectly absorbs everything, and then this filter which actually controls the overall spectral performance. So we need to build this, and then in building this, people have attempted many different ways and have failed. So what has happened in the past is um, most of the efficiencies have been less than about 15%. There's only one record, I think, which is still about 20, 25 years old, which has shown a true experimental efficiency of about 18%. And recently, there has been claims about indirectly estimating efficiencies close to 30%, but nothing really has materialized in reality. Okay, so the efficiency that way has still remained quite low. So why is the efficiency low? The reason why efficiency has not achieved or gone beyond maybe 8%, especially with nanophotonic designs, is that the optical losses of all materials, no matter what material you pick, they all increase at high temperatures. Okay, and at high temperatures, light confinement is also very hard. You cannot confine light to nanoscales that is necessary for you to create that filter functionality. So that's why we haven't been able to make this better. So what we said was, okay, let's try studying the system, find out what is really needed to make this work well. Okay, so one of the alumnus of BUET, in fact, Sakib, so he worked with me on analyzing the system. So what we did was, let's say we take this selective thermal emitter, okay, so which is just an emitter that is operating at very high temperatures. So it has some heat, so it's maintained at some temperature, and it also has the filter functionality. Okay, so here is the filter functionality associated with it. That is, it doesn't emit light in all wavelengths, but emits only in some wavelength where this filter has a large passband or transmission through. Okay, so let's call this transmission or emission. It's called emissivity, in fact, as rho. And then let's call the bandwidth of this emission delta. Okay, and then in the regions where we don't want this filter to emit, of course, it cannot be zero. That's ideal. So in non-ideal case, you have some very small emission. Let's call it S. Okay, so S is in dB. And then we have on the other side just a normal PV cell. It might not be silicon. Actually, this is not submitted now. It's published. Sorry about that. It's published in Applied Physics Letters. So now let's model this. So what would happen? So here is what we found out. So we found out that the suppression, and here is the emission, the passband emission. So in the passband, suppose let's say we have perfect unity emission. Then in the suppression for the long wavelengths of infrared, we want the suppression to be at least about 20 dB to see efficiencies close to 30, 40%. Okay, so that's why people haven't achieved that high efficiencies, because most of the suppression in the past work has been close to 5 dB. So this is something that our analysis really gave us an insight that People have been focusing more on getting perfect emissivity, but that's not the problem. The bottleneck is actually the suppression. That's where people have failed in the past. Okay, and then further, if we also increase this emissivity not just to 1 but beyond 1 by using techniques like concentration, like take a lens for example and then concentrate light from a large area of this emitter into a small area of PV cell, then we would get additional improvement in enhancement just like PV cells, and we can easily get efficiencies close to 50% absolute. Okay, so this is efficiency normalized to Corona efficiency at this particular temperature. So absolute efficiencies can go up to 50%. So we were really excited. And this is in fact practically possible. We have chosen very practical conditions for this model. It's not anything ideal or anything that is not possible in labs. So with this, we were like very excited. So how to do this? How to achieve this good selectivity? So that's the problem we have in front, and that's a clean opportunity for nanophotonics to contribute. So how do we do that? So let's take think of a perfect cavity. Okay, so whenever you want some selectivity or design a filter, you think of a cavity which acts like a resonator. So which means the photons, this is a mirror and here is one more mirror. So the photons just go around and around in this cavity many times and then gives rise to the resonant phenomenon. Okay, so at resonance, you would have a perfect emission from the cavity and then otherwise not. So suppose, let's say for the photon source, we put a thin layer of some emitter. It could be some material that has loss in it. So any lossy material, if we heat it, will emit thermal photons. So now this emits thermal photons in broad wavelengths, but only photons that have the right conditions for the cavity resonance, they will just go back and forth in this mirrors or between these mirrors many times and give rise to selectivity. Okay, so if we choose, for example, this material as tungsten, we can get a Q factor of close to 45. So Q factor is basically a quantity that captures how good the spectral narrowness is. Okay, so we can get really narrow and then hence huge suppression in the regions where we don't want photons to be emitted. So we can get roughly, you can think of this as that selectivity S. Okay, so in terms of dB, this is roughly about how much? Some 16 dB or something like that. So that's what tungsten gives me. And then this is ideal tungsten. So if you use instead semiconductors, you can get selectivities that are much larger. In fact, getting beyond 20 dB is not difficult. You can get like 25, even 30, 40 dBs of selectivity with the semiconductors. Okay, so this was really exciting that you could do much better than what people have done so far by using combinations of metals and semiconductors. The semiconductors are extremely promising. Okay, the only problem with just using semiconductor is if you were to have really small loss in your system, like the case of gallium arsenide, very lightly doped gallium arsenide, the loss is small, so you have very high Q factors in the system. So this is Q factor, you have very high Q factor, but the peak emission from the system, that is the rho, the spectral brightness, that will be small. So on the other hand, if you increase the loss in the system, you would get very high emission, but the Q factor, that is the suppression, now becomes worse. So there's a trade-off between these two. So how do you achieve the best? So how do you get the sweet spot? Okay, so for that, that's where I think a lot of previous designs have failed. So they have done either one of them, like very high brightness, or they have done very good suppression, but not both. So how do you hit this sweet spot? So we said, okay, let's not take this approach of where we considered light as just waves and then use some electromagnetic simulation based on Maxwell's equation. That was all classical. So on the other hand, thermal emission itself, the whole problem of thermal emission gave rise to quantum theory, right? So in 1900, Planck's paper just said that thermal emission cannot be explained unless we quantize the energy of photons or energy of light. So that's how quantum theory was born. And Einstein later proved that yes, quantum theory of light is in fact true, and light in fact behaves as a stream of particles, right? So later, of course, we know Bohr's model. So all of this led to the birth of quantum theory, but we almost completely forgot about the quantum nature of light in thermal emission. Okay, so we have been only looking at the classical physics part, which is controlling the density of states or photonic density of states. Almost never focused on the quantum property of photons. So what if we use that and bridge these two regions? Can we do something better with thermal emission control? That's what my group started out with. So we said, okay, the past designs like metamaterials, plasmonics, photonic crystals, they all focused on only the photonic density of states. Let's do something more than that. So where people focus on single resonator design, can we do something beyond that? Okay, if we want to bring quantum nature of light, we now have to describe the quantum property of light. And we know that Hamiltonians, for example, help us do that. So in the past, all the systems that we have considered were all closed systems, meaning their energies were conserved. We had observables and they had real eigenvalues, right? So that's what we really learn quantum mechanics about. We never learn almost anything beyond this. Okay, but thermal light source is not that kind. So whenever you have photons that come out of a source, a light source, it's an open system. There's exchange of energy, right? So the energy is not conserved, and not always you have observables, and then you are not guaranteed to have real eigenvalues. So then your Hermitian systems, that is your Hamiltonians, which were Hermitian in the case of closed systems, are no longer valid, and you require non-Hermitian physics to describe thermal emitters. Okay, so that's what we started doing. So non-Hermitian systems have additional advantages. So what are they? In the past, we had only materials and geometry as tools of design. But now with quantum description, we now have phase, symmetry, and topology, which are extremely powerful tools that classical engineer didn't have. Okay, but now with quantum approach, we have these powerful tools to control thermal emission. That's how we should be able to achieve that huge suppression and then also a large emission enhancement. So that's the idea which really inspired us further. So a particular class of non-Hermitian systems are known as parity and time symmetric systems. Okay, so I'll just introduce this only because this is very interesting and we make use of this. Okay, so when I say parity and time symmetry, let's take a two resonator system. So I have one resonator here, another identical resonator, and they both are coupled by this coupling constant kappa. Okay, so let's assume that this resonator has some optical gain. So just like lasers, so it amplifies light in it. And the other resonator has an equal amount of optical loss in it. Okay, so this is loss and gain in the system, but balanced. So this, because it has loss and gain, the system is no longer a conserved energy system. So it's an open system. Okay, we can write the Hamiltonian of the system simply by just this 2x2 matrix. You have one lossy resonator, another a resonator with gain, with the gamma as the loss and gain component here. Okay, and kappa is a coupling between these two resonators. Very simple. So what do you mean by parity? So parity is mirror symmetry. So if I have a mirror across at the center, which means I would exchange this gain and loss resonators, so that's parity operator. So now if I apply time operator on this, so time operator will, in the case of optics, will turn gain into loss and loss into gain. Okay, so now I got back this loss resonator here and gain resonator here. So with both parity and time operator, I just restored back whatever I started. Okay, so that's why this system is parity and time symmetric systems. So in 98, Carl Bender and Bocher, so these two people, gentlemen, scientists, they proposed that such systems do have real eigenvalues. Not necessary that they have imaginary eigenvalues or complex eigenvalues, that they can have real eigenvalues as well, just like Hermitian systems. So which really spurred interest in the community. A lot of people started investigating this. And in nanophotonics, we were really curious if this works. So that's what we started out with. So if this works, here is what the system should look like. So when we have this kappa, okay, extremely large, really huge number. So then these two resonators are so closely, so tightly coupled to each other that they exchange energy between them so fast that so fast or faster than the losses in them, that the modes are almost equally spread between these two resonators, this loss and gain resonators, and I just get two different real eigenvalues for this system. No imaginary, just two real eigenvalues. Okay, but if I start decreasing this kappa, then these two eigenvalues start to approach each other, and when kappa is equal to this gamma, at that point, you see that the eigenvalues just coalesce into just single. So that's degeneracy point. Okay, if I reduce kappa further, the eigenvalues just becomes complex conjugates. So they're no longer just real, but instead they have a single real part, but two different imaginary parts, or equal and opposite imaginary parts. Okay, this is extremely important only because now I have two modes in the system, one that has huge loss, another that has gain, another that is growing in time. So the loss one can actually get my thermal photons out. I need optical losses for thermal emission. So thermal photons come out from the loss resonator, while the gain resonator can actually take these photons and store in it or amplify it. Okay, so this is really the cool part of PT-Symmetry, which is what really inspired us in designing thermal emitters. Okay, so this phase transition between these two regimes, PT-symmetric phase and broken symmetric phase, so that point is known as exceptional point. It is called exceptional because it actually has exceptional topological properties. Okay, we'll see that in a minute what it means. Okay, so how to design this? So in fact, for thermal emitters, we don't need gain. There is already thermal photon source, so we just need only loss and then no loss. So that's called passive PT-symmetric systems. So we designed such a passive PT-symmetric systems by having a tungsten resonator, which is extremely lossy, and then here a silicon resonator, which is almost nearly lossless. And these two resonators couple via a magnesium fluoride spacer. Okay, so if I change the thickness of this magnesium fluoride, I change how these two resonators couple with each other. Okay, so now I can have a system where all the thermal emission photons, they come from tungsten while they're effectively stored in silicon. Okay, so that's the idea here. If you have any questions, please stop me anytime, no problem. Okay. Okay, so we did model thermal emission from the system using a simple circuit model or transmission line model, in fact, which makes use of lumped elements. And we saw that the thermal emission does show the same behavior, which is when the coupling constant is really high, we have two different modes or emission modes from the system with nearly the same Q factor. But once we go to this PT broken regime or small coupling constant, we see only single mode in the system, which has its brightness nearly unity. So its peak thermal emission is almost constant at unity, and then or constant emissivity or very high brightness, while the spectral selectivity or this spread of the emission becomes narrow and narrower and narrower. Okay, so we basically have very high brightness, but at the same time, very good Q factor. So we did even take the system and simulate this and using full waves, that is full electromagnetic simulations, and then found out, yes, we do have the same behavior. That is, our emissivity of the system is nearly unity, while the Q factor just continues to grow and grow if we reduce the coupling or increase the spacer thickness. Okay, so this was clearly something, if we go back and think about the trade-off that we had. So if you remember, in a single resonator system, either we had good emissivity or we had good Q factor. We didn't have both. But in this system, we have constant emissivity of 1, while our Q factor continuously increases. So we broke the trade-off between Q factor and emissivity. Okay. So we did make this system by just having this tungsten, magnesium fluoride, and then here silicon discs, just all made out using electron beam lithography. And then we put this sample in vacuum chamber and then heated to very high temperatures here, in fact, 700 degrees centigrade. And then we measured the thermal emission from this using a Fourier transform infrared spectrometer. Okay, so using that system, we did see that the system exhibits PT symmetry. Again, I think I wanted to emphasize one thing. To get PT symmetry, we require modes that are localized in this silicon and tungsten resonator system. So here we see an array of this resonators, but we don't want an array. We actually want modes that are localized in individual resonators, not spread in this whole sample. And how do we do that? Is actually using a concept known as bound state and continuum. I won't explain that in very much detail, but if we were to look at the band structure of this periodic system, we see that there is a flat band. Okay, so there is a band that has nearly flat dispersion, means that it is localized. So in real space, it is just localized in a single resonator. So in experiments, we see that all these modes don't show any angular dependence, so which is an indication of this flat band, and hence we do see individual modes in the system or localized modes in the system. Okay, then we experimentally measure the thermal emission. This is actually measured thermal emission spectrum at 700 degrees centigrade. As we change the thickness of this magnesium fluoride layer, when we have 0 nanometer that is very strongly coupled, we see two modes. But as we increase the spacer thickness, these two modes merge into one and then eventually just become a single mode whose Q factor in fact reaches 40. And 40 is by so far the highest recorded at this particular operating temperature. And it's only limited because every material becomes lossy at high temperatures, including silicon. So that losses limit the overall Q factor eventually. Okay. Okay, so with this, what we could do is we can get really bright and high Q thermal emission. So we break the trade-off, as I mentioned. And how does that happen? So if we look at the simulation profiles, so here I have what is known as divergence of Poynting vector, which shows where the thermal photons are all coming from. They all are coming from tungsten, which has a loss in it. But the thermal photons are stored equally in both plasmonic and photonic modes in the case of 0 spacer thickness, magnesium fluoride thickness. But if we increase the spacer thickness, still all the thermal photons come from tungsten, but they're stored mostly in the silicon's photonic mode. Okay, so essentially what is happening is all the photons come out from tungsten and they're nicely stored in the silicon resonator, where the silicon resonator leaks these thermal photons only in a very small spectral window, which makes our filter functionality. Okay, so we have a tungsten heat source which just emits for thermal photons in all wavelengths, but it's silicon which actually gives us the spectral selectivity. So we get the best of two worlds, that is the bright and high Q thermal emission from the bright from plasmonic and then high Q from photonic resonators. So that's best of both the worlds. Okay. So not just that, we can also get directionality from this if we increase or if we change the angle of incidence from normal to slightly off normal, then we see that the system exhibits some very interesting property. It's no longer just a 2x2 system, but actually a 4x4 system. Our system actually has a vertical mode as well in silicon. They all couple and then in fact give rise to a very interesting topology known as exceptional concentric ring. And on this concentric ring, we will see that the emission will be really bright and then anywhere else it will be dull. So we actually get very good directionality as well. So only in certain angles we see huge bright emission and then not in others, which is what we need for making very good thermophotovoltaic system. Okay, so overall what I can tell you from whatever we have done so far is we can easily get this Q factors close to 100 in the case of this non-Hermitian thermal emitters. So that corresponds to about 20 dB broadband suppression, which was not shown any time before. Previous demonstrations were only just about 5 dB. So now we can get close to 20 dB. And then with directionality and then bright emission, so directionality actually allows us to have concentrations, for example, use a lens and then focus light down to a small region, then we can get easily 100 times concentration with this. So overall, with these two things, we think we can hit efficiencies close to 50% while just operating at this low temperature of 1300 Kelvin. Okay, so this is revolutionary for many applications. In fact, what we have been currently working on is actually working with NASA on an application in space. So where they want to use this as a primary source of energy generation on Moon. So the next goal for NASA is to build a base on Moon, a lunar base. And for that, they think this thermophotovoltaic conversion, again using in fact materials like carbon nanotubes, would be extremely interesting, and that's what we are currently working on. Okay. So that's just the first part of phase transition that I wanted to discuss with you, where photonics or light can make a huge impact to our society, not just the society with terms of energy, current energy situation, or global warming, but actually even enable applications like space, where we can colonize perhaps even Mars sometime soon. Okay, so that's what nanophotonics can enable us. If you have any questions, I can take at this point. If not, I'll move on to the next part of the talk, where I'll focus on an electronic phase transition coupled to light, okay, which enables tunable optical devices that are necessary for displays. Okay. Okay. So what is nanophotonics currently doing? So you see a lot of new applications coming up. In fact, so many startups that I see here in the US, where the people who are saying we can make meta surfaces that can enable LiDAR. So our vehicles, autonomous vehicles, vehicles that can drive without any drivers in it, okay, which requires LiDAR or light-based detection of what is around them. And for that, we require tunable, very compact nanophotonic devices. And then displays, okay, you know that our current displays are 2D, can we make it to 3D? So can we make a hologram that's moving, that can change over time? So which requires tunable optical devices. So virtual reality, artificial visions, they have been extremely fast developing, especially with gaming, and then even in theaters. Those our vision has completely changed. The way we see things have totally changed in the past, especially with drones and virtual reality. And they all badly need tunable optical devices. So how do we enable that? Okay, many different ways to achieve tunability. I have just listed a few. Okay, so field effect modulation, you apply some voltage on some materials like semiconductors or graphene, then their optical properties ever so slightly change. So that's one way. You can also stretch or mechanically deform something, even in the case of MEMS, and that will change the optical properties like reflection angle. You can use liquid crystals, where just by changing the temperature or applying a bias will change the phase, the way molecules orient, then hence the refractive index. So that's another way. Elastomers are also something very similar. Okay, you can also use chemical techniques like apply a voltage, then electrochemical reactions will change the optical constants. You can use photochemical chromic effects, where you shine light that will initiate some chemical reaction that will change the optical properties, etc. Many different ways. Okay, but if we look at what happens in all of them, they're either extremely slow, like for example, this electrochemical reactions, etc. They all are very slow. They take seconds, a few seconds to achieve this tunability. On the other hand, you have things like field effect modulation, which can be really fast, like gigahertz, or nonlinearity, which can be even ultra fast, like terahertz. But still, they're very tiny in their tunability, and you cannot get very large tunability. If you want to get both fast and large tunability, you have to take a very different approach. Okay, in conventional materials, the tunable response comes only because light interacts with single particles, fundamental particles, like for example, single electrons in this material. An electron absorbs light and then makes a transition in its energy levels, changes optical constants. Okay, but what if we have quantum effects? So meaning where you have many particles interacting with each other. So when light causes or interacts with this material, it will not just interact with single electron, but simultaneously interact with many electrons in the system. So that can give even larger change in optical constants. So what if we study quantum materials or use quantum materials for this purpose? So that's what my group was really excited about. We started investigating this. We actually were surprised. There was no result available in literature that did study any quantum material with light. Okay, so we started looking at tantalum disulfide, so which is actually a 2D material. So it exhibits as single layers of tantalum disulfide that we can mechanically peel off, okay, mechanical exfoliation. Peel layers of them and then study what happens to this. So in the past, people had shown that this material exhibits a huge change in its electrical properties, even at room temperature, okay, because of this strong correlation. these materials exhibit something known as charge density wave, or CDW. Okay, so which means now here, for example, 13 tantalum atoms, they slightly move inwards to make the star-like structure where they carry single charge in it. So now there can be many such single charge domains which all interact with each other as if like collectively, or through coulombic interactions, as if like they all are tied together by charges. Okay, so that's called a wave, charge density wave. And at room temperature, this material still exhibits such kind of stars, but now in small domains like this, which are known as domains of CDW, or CDW domains. Okay, so these domains are existent, or they exist in each of the layers of this material, and they change as we apply different stimulus. And that's why they show this huge tunability. So we said, do optical properties change? They also change with respect to which stimulus. Electrical properties change. What about optical properties? So we took 80 nanometer thick film of this tantalum disulfide, created here electrical contacts, then applied DC bias, okay, and then we see that the optical constants change a lot. In fact, this is change in the order of or refractive index change in the first decimal place. That's huge. Okay, most of the materials like graphene, for example, or even other fast changing materials, you would see their changes only in third or fourth decimal places. This is first decimal place. That's huge. So we also saw the same change with AC bias. Just AC, very small voltage. This is just 0.5 volt, the amplitude. And we see this huge change in refractive index. We are like really surprised what is happening. And even pleasantly excited, surprised about this discovery. So we wanted to see what if light is causing something to it. Maybe we are shining light on the system. Maybe that's doing something. Let's see. So first we took very low intensity light. So if I want to say quantify this intensity, it's just zero 0.1 sun solar intensity. Okay, if you take the sunlight intensity at noon and then take only 1/10 of this intensity, that's what we took. Okay, so 110 sun now gave us the optical constants of this material. So this material has two different optical constants. So one is in the plane of the layers, the other is out of plane of layers. Okay, so overall, this optical constants just tell me that this is a very lossy and absorbing dielectric. That's it, nothing special about it. Okay, it's just any other dielectric, but with very high dielectric constant and also very high absorption in it. But what was really cool about it is, I think I have a question. Uh, yes, okay. I think there's a question sorry, I didn't see about the previous part of the lecture. If you don't mind, I'll take it at the end. Please excuse me for that, okay? Okay. So what we saw was when we changed the intensity of light, then this material showed its optical properties to change, but only in oblique incidence. So here is normal incidence where the reflectance doesn't change with intensity. But in oblique incidence, I see a small change in reflectance. And this is actually huge for this material, given that it's only very tiny. In fact, this sample that we took was only about 20 nanometer thick. And 20 nanometer thick giving this huge change in reflectance was very surprising. So what is happening? So we extracted the optical constant. So since oblique incidence only changes refractive index, it must be changing only in the vertical direction, only across layers. That is this direction permittivity. So we extracted, excuse me. So we extracted this permittivity as a function of intensity. Okay, so here 100 milliwatt per centimeter squared, this is just one sun intensity, and we're using white light. This is not lasers. Okay, no lasers in here, just white light. And then about 1 sun intensity, we see already such huge change. This is 10 sun intensity. We go from 0.1 sun to 10 sun intensity, and there's huge change in optical constants. And we wanted to see how fast is this. So we took a laser and modulated it with, in fact, this was first we took a picosecond laser and then saw that the response of the system was actually in hundreds of nanosecond, close to 300 nanosecond. So we then took another laser, chopped it at microsecond or even at kilohertz frequency, and then did a systematic time domain measurements to explore that this material actually has an electronic response that is on the order of 300 nanosecond, 300, excuse me, yeah, 300 nanosecond. Okay, so that was really fast. So which means we could probably operate this at a megahertz. So this is a megahertz tunable material with large tunability. So why is this happening? So we said, is this because light is being absorbed and it generates free electrons in this material? We did some calculations to say that no, that cannot be. It's just too few electrons that are produced in this. It's a very tiny. Okay, and then what about nonlinear optics? So we didn't see any higher harmonic generation, so we ruled out nonlinear optics. Is it any photothermal effect? So when I say photothermo optic, I mean photothermal or light causing heating in this material, which eventually changes optical properties. Is that the possibility? We did a thermal model of the system with a very lenient parameters and saw that the temperature increase could not be more than 0.5 degrees. Okay, so with especially white light. So clearly it cannot be this effect to see that huge change in optical constants. So then there must be something related to this charge density waves or collective electronic mode in the system. So then what we did was we hypothesized based on some other recent works, we said, okay, maybe this is what is happening. The optical constant change only in the direction across layers, that is in out of plane, not in plane. So maybe it's something related to do with how this CDW domains stack on top of each other. Okay, so let's consider this gray domains, which are all stars in one layer, bottom layer, and in the top layer we have this blue or this red stars. Okay, so hollow stars are in the top layer. So now the stars can align on top of each other in two different configurations. So one is on top of each other, like this red case, so which is center to center stacking. The other one is they can stack center to corner, or the staggered stacking case. Okay, so the staggered stacking case has lowest Coulomb energy, and hence that's the ground state. And this red one is the upper state. So we thought, or we said, that the absorption of light actually causes the stacking to change from this blue one to red one. That's why we see tunability. And we think when this blue domain absorbs light, then this whole domain exchanges or shares this energy of a photon and then eventually just vanishes. Or this CDW formation just dissolves. And then eventually it will emerge in this red configuration, which is what is giving rise to tunability. This was just a hypothesis. Okay, so what we did was we built a 3-level model to explain this. It's just a phenomenological model. So this is the excited stacking state, this is the ground level stacking state, then here is our white light causing transitions. Okay, we in fact measured all the time constants from our experiments and then found out or expected from this model what should we expect, or what fraction of the domains we should expect in this red stacking form or this excited stacking order. Okay, so then that's plotted here for different white light intensities. And then now we can use Maxwell-Garnett effective medium theory to predict the optical constants. So what we did was, to our surprise, the predicted optical constants were such a good match with experimental ones. So the solid lines are experimental ones, and the dotted lines were predicted from this model, from this theory. So they are such a good agreement that we were really convinced that the model, the hypothesis is true, which is the mechanism of tunability is actually this, that light causes the CDW stacking to change in this material, which is completely a new thing for people in this field. They never thought that stacking, or how the CDW domain stack on top of each other, could be another phase of this material, electronic phase of this material. So that's what we showed. So a phase transition in this material caused by light changes its optical constants. So that's about interesting science. Okay, there are a lot of now new questions about, oh, if this is the case, then what happens if we put something on top of this material? Will it still change? Now, this charge density domains, they all talk to each other. Can we, for example, control this, how they talk to each other with light, and thereby make this material superconducting? Is that possible? So in fact, there are theories that says, yes, it could be possible. So we think light could be now a tool to induce to make this material a superconductor, a 2D superconductor. Okay, there are so many new physics questions that arise from this, but from the engineering point of view, there are again a lot of things as well. So we just made a simple, not even an optimized, just a simple grating. Okay, and then we looked at its diffraction strength. We see that this diffraction strength changes with illumination intensity. And this intensity, look at this, this is just one sun intensity, 100 milliwatt per centimeter square. Just with one sunlight, I can actually change the diffraction strength from this device. Okay, we further optimized this device a little bit and then made a meta grating which is blazed. So when I say blaze, it has only +1 grating order compared to, or +1 is more enhanced compared to -1. Okay, as you see in here. So that kind of blaze grating we designed. And then what we see is this blaze grating design device actually shows megahertz. So this is 10^3 kilohertz. So this is a few megahertz bandwidth. And at the same time, it has 100% modulation depth. So the diffraction efficiency goes to about 50% just with here 10 milliwatt per centimeter square, not even 100, just 10 milliwatt per centimeter square, that is 0.1 sun. So it's ultra low power operation, 100% modulation depth, megahertz bandwidth, and no moving parts. That's like the ideal thing that one can expect for applications like sensors or lidars on drones, right? So that's what we think our device can enable, and we are currently working on building one such tunable meta surface. So I just want to wrap up my talk saying that this phase transition or electronic phase transition in tantalum disulfide is extremely promising for tunable nanophotonic applications, and then has many new interesting physical phenomena associated with it. The tantalum disulfide is just one such material. There are many, a class of such materials, in fact, which hold promise for future nanophotonic applications. Okay, so with that, I would like to thank, of course, all the funding agencies like NASA, Army, NSF, even Applied Physics Society, which all helped me do this. And of course, my students, particularly Chloe, who did the first part of the work, and Sakib, who did the TPV part of this work, and then also Weijian, who did the tantalum disulfide part of work. Okay, and thank you all for listening to me, and thanks Sajid for inviting me to this to this Day of Light or International Day of Light celebration. Thank you.
Thank you so much, Guru. It was a fantastic and very fascinating talk we could see, and hope everyone of the audience really enjoyed and was really curious about what these things could do technology-wise. And now the floor is open for question. I see one question from Dr. A.S.M. Mohsin. So, Dr. Mohsin, if you could, you can unmute and ask the question yourself.
Yes.
And Dr. Mohsin, are you there?
Hello. Yeah. Uh,
Okay, maybe I can read out the question from the chat box.
sure. Sure. Go ahead. Yeah.
So the question is, could you specify why you use tungsten, and why did you check with other materials, and is the device experimentally tested? I actually had a related question. So, Guru, you
Sure.
pioneered the field of titanium nitride in Purdue along with Professor Tim Stann's student. So, did you think about using titanium nitride as the resonator and silicon nitride as a spacer layer for your structure, or what was the motivation behind using tungsten?
Sure, sure. Yeah, that's an excellent question. And thank you, Dr. Mohsen, for this question, and Sajid for the follow up. So, the first thing is we wanted to, this is a device that's going to be operating at high temperatures. So, I'm actually, I mean, in my experiments, I took this chip or this device and then heated this to 1300 Kelvin, or close to 700 degrees centigrade. Excuse me, not 1300, 700 degrees centigrade. So this a lot of materials don't really stay well at this temperatures, like gold, silver, aluminum, all of them just degrade at this temperature. So we wanted something that's refractory, and then tungsten was a good choice because people had worked with them before. Tungsten, tantalum, molybdenum, all of them. And then for Sajid questions, why not titanium nitride or Zirconium, in fact, in my PhD, I did show zirconium nitride also, titanium nitride, and few other nitrides, hafnium nitride, etc. Those can be really excellent refractory materials. So we could use them as well. So just I think for our, at least I was just starting at RISE, and then as many of you know, titanium nitride or zirconium nitride, these are not standard materials. Like you cannot go to market and then say, okay, get me a chip of, or a thin film of titanium nitride. Instead, you have to actually optimize the growth condition, maybe have a sputtering machine, then sputter this material. So I was in a process of building all these things at RISE where there was no such standard thing available. So we thought, okay, let's begin with tungsten only because it's easy. But recently, I didn't talk about a few other recent papers that we have. Very recently, we have our work on using zirconium nitride, where we see even better performance. In fact, zirconium nitride makes this device operate in all of the broad wavelength ranges, starting from like 500 nanometer in the visible all the way to 20 micron in the infrared. So it's that broad wavelength range that we cover with just zirconium nitride. Okay, so tungsten is great, of course, but it doesn't work in the visible. It's just too lossy. But zirconium nitride is even better. So we just still have some simulations and yet to build a device on zirconium nitride. But tungsten one, we already have a device, the thermophotovoltaic device, that shows the overall energy conversion. So that's something work in progress. We have a chamber, a vacuum chamber, tested the emitter device as well. Then we also have a PV cell, but we haven't put them together, and that's what my students are currently doing.
Okay, thank you so much. And is there any other question from the audience? We could have a couple of more questions if anyone wants to go ahead. So I see a question from Asif Hussain. So Asif, you can go ahead and unmute and ask the question.
Thank you for your wonderful presentation. I am Asif Hussain, recently graduated from BUET. Actually, my question is about the phase transition. Is the phase transition non-volatile?
The phase transition is, first of all, I should say both of them are reversible. Okay. So that should answer you. It's not like non-volatile. You can hold it, of course, but they're reversible as long as you have the stimulus. In this case, in the second case, light shining on the system, or in the first case, you have your spacer thickness that is exceeding a particular limit, then you would retain that phase. But you can always bring it back just by reversing the stimulus.
Okay, thank you.
Thank you very much, Asif. Is there any other questions from the audience? If not, I would like to really once again thank Dr. Gururaj Naik for his time and excellent presentation today. And with this, we have our first webinar on behalf of both the IEEE Photonic Society Bangladesh chapter and the Optical Society of America Bangladesh section. So thank you so much for everyone for joining with us. And Dr. Naik, thank you so much for your talk and time. So I would, with your permission, I would like to conclude the session and thank everyone for coming today.
Sure, yeah. Thank you very much. And I look forward to meeting you all in future, probably in some conferences. Thank you.
Okay, thank you. Have a good night, everyone.